Depictions of daily life scenes where the human nature is secondary when confronted with the majesty of the architectural elements. That of the View Painters is a movement originated around the 16th century in Belgium and that focused at first upon detailed representations of cities and landscapes, and that would later come to include imaginary elements as well. And it was under these premises that I started playing around with the idea of creating a sort of a system that would allow me to reproduce something with the same vibe but in 3D. By observing the work of the masters, we can see the same architectural elements appearing over and over in all of their different paintings, but every time readjusted to the specific context and composition. Is this kind of proficiency something that we can achieve in 3D as well? The answer, of course, is yes, and it lies in the concept of modularity. Whatever it is that we are exploring, we need to break it down into its main constituents and then take these constituents and break them down even more. And when we take this concept of modularity and we bring it into non-destructive workflows, we basically open the door to the possibility of creating countless different scenes, where the focus will be more on the artistic side rather than on the technical aspects. In the following sections, I'll show you a couple of useful techniques to create these building blocks and assemble them into composite structures. We'll look at how to procedurally build some of the most iconic elements like columns and vaults, and I'll also show you how to generate procedural damage without using any external add-on. At the end, I'll put everything to use in creating a simple scene. We can start this journey by looking at how to build a procedural columnade. For that, my requirements would be to start by creating a single column with a defined height and with a shaft composed of several different drums of random sizes. I'm going to start by creating a single drum, and for that a simple cylinder will be more than enough. We want to have the origin point right at the bottom, so in edit mode I'm going to select the bottom face, then Shift S and move cursor to selected. Then in object mode, right click and set origin to the 3D cursor. In this way, whatever scale we apply along the Z-axis, it is going to be applied from the bottom to the top. I'll then move the cursor back to the center of the 3D world with Shift-C, and I'm going to move there my mesh as well, again with Shift-S and selection to cursor, in order for it to be standing exactly on the ground. The other thing that I want to change is that currently we do not have a one-to-one relationship between the scale and the dimension of the object, since for a scale of 1 unit we have a dimension of 2 meters. In order to amend that, I'll select all of the 3 axes and set them to 1, and then Ctrl-A and apply the scale. Suppose that I want my drum to be 5 meters tall, I can now just type 5 here into the scale system and it will correspond to a height of 5 meters. I'll set this back to 1, rename the cylinder into drum, and I'm going to create as well a collection that will contain all of the instances that will belong to this column system. At this point, I'm going to right-click my mesh and shade smooth by angle. And I'm also going to add a cube that will act as the holder or controller of the geometry node system. Speaking of which, let's open a tab here at the bottom to visualize the geometry node editor. Then I create a new system and I remove the existing connection. I'll split the top view as well to visualize also the spreadsheet, and then I'll take my drum, bring it into the geometry node system, and I'll disable its collection in the outliner. Now, the easiest way to stack a mesh multiple times along an axis is by using a mesh line node, and we can use this to produce the points upon which our mesh will be instanced. In our case, if we take our drum and we connect it to the instance socket of the instance on points node, and then we connect this to the output, we can see that we are stacking a mesh a given number of times on the specified axis. Our drums are currently stacked exactly on top of each other, and that's because the mesh line node comes with a default offset of 1 meter, which is the exact dimension that our object has on the Z-axis. But what we need to have is a different dimension for each of the drums, and to do that we will need to use the accumulate field node. What the accumulate field node does is to increment with every iteration of the index, based on whatever value is used as an input. In our case, we have 4 points in our mesh line node, hence we will have 4 values for our index, and for each one of those, the output of the accumulate field node is increasing by 1. The same logic is true also for the trailing output of the node, with the only difference that instead of starting from 1, it will start from 0, while the total output will represent the total accumulated value just repeated for every iteration of the index. I'll add a random value node to the tree and I'll feed it into the value input socket of the accumulate field node. And the concept here is very simple. I want the size and positioning on the Z-axis for each of the drums to be driven by these values. For instance, for the first drum, which is instanced at an index of 0, I want its size on the Z-axis to be the difference between the value at the next iteration of the index, which is in this case 0.86, and the value at its current index, which is 0. Then I want the positioning on the z-axis to be driven by the value at its current index against 0, which means that the drum will be placed exactly on top of the floor, and the same logic will be applied iteratively to all of the other drums as well. Given that, I'm going to add a math node, set it to subtract, and I'm going to subtract the leading and the trailing values coming from the accumulate field node. Then I'm going to add a combined XYZ node with all of the values set to 1 for the moment, and I'll connect it to the scale input of the instance on points node. I'll then take the output of the subtract node and I'll connect it to the Z socket of the combine node. And you can see now that we have a different size on the Z-axis for each of our drums. We now need to change the positioning of the drums on the Z-axis according to their new respective sizes, and to manipulate the points I'm going to add a set position node in between the meshline node and the instance on points node. I'll then use another combined XYZ node and set all of the three values to 0, and I'll feed it into the position input of the set position node, and all of the drums will collapse to the center. I'll then take the trailing output of the accumulate field node and feed it into the Z socket of the combine node. Now that the drums are stacked exactly on top of each other, another thing I like to do is adding another subtract node to the chain here with a very small value to create just a little gap and make this whole idea of the separation between the different drums even more visible. What we need now is to get control over the height of the shaft, which is currently randomly determined by the number of drums and by their respective sizes on the Z-axis. Suppose the desired height of the shaft is 8 meters and that the current height of the shaft, which we can derive from the total output of the accumulate field node, is 4 meters. If we take the ratio between the two, we get a proportion of 2. And if we now rescale each drum by this very same proportion and we make sure that each drum is stacked on top of each other, we can go from the current height to the desired height. Hence, I'm going to create a new math node and I'm going to set it to divide. Then I'm going to drag one empty input socket from my group input node and I'm going to place it at the top. And this will represent my desired shaft height. I'll then take the total output of the accumulate field node and place it at the bottom. Let's assume that the desired height for the shaft is 6 meters. In order to rescale each drum accordingly, we need to reproportion their original sizes before the application of any gap by the factor identified within the divide node. To adjust their positioning on the z-axis, we need to take their original position as well and multiply it by the same reproportioning factor. We now have control over the height of the shaft, and all of the drums will fit into that value despite their number and their individual sizes. I'm now going to create a couple of additional input parameters, one to control the gap between each drum, and one to control the minimum and maximum potential sizes of the drums on the z-axis. For the moment, I'm going to set the shaft height to 6 meters. Then I'm going to change the number of drums to 3, and I'm going to make the minimum potential size 0.5, while I leave the maximum potential size to 1. Apart from the height of the shaft, I also want to be able to control its thickness. And that's pretty easy. We just need to create another input parameter and connect it to both the X and Y sockets of the combined XYZ node connected to the scale input of the instance on points node. I'll rename it to shaft thickness, place it right below the shaft height, and check that everything is working as intended. We now need one final adjustment for our shaft to reflect the fact that columns are usually tapered at the top. And in order to understand how to implement this into a geonode system, we are going to do a practical example. I'm going to disable the controller and enable back the collection containing the drum. I'll then create a temporary copy, tab into edit mode, select the top face and scale it down by a factor of 0.8. Suppose that I want to have 4 drums in my shaft. In order for the tapering to be applied uniformly, I will need to create a new drum, place it on top of the first one and scale it on all of the axes by the z-axis by the same factor that I use for the scaling of the top face of the first drum. In this way, the size of the bottom face of the second drum would equal the size of the top face of the first drum, and the relationship between the sizes of the top and bottom faces of the second drum would be the same as for the first drum. I'll repeat this process another time by adding the third drum, and again I'll scale it on all of the axes by the z-axis by 0.8. And I'm going to do that another time for the fourth drum. We can see that in this way the tapering is applied uniformly from the bottom to the top. And if we select the 4 drums and we look at their respective dimensions on the x and y axis, we can tell that these are all powers of the original scaling factor. And in fact, for the first drum, we have a dimension of 1, which is 0.8 at the power of 0. Then we have 0.8 at the power of 1, 0.8 at the power of 2, and 0.8 at the power of 3. Back to our geometry node system, we need to understand how to select the top face of our drum and scale it by the desired amount. To do so, I'm going to take the object info node that contains our drum and I'm going to feed it into a scale elements node. We know that each vertex, edge, or face has a specific ID, and so I'm going to add an index node as well as a compare node. I will set the latter to integer and to equal. I'll then connect the output of the index node to the top, which will allow us to scroll through the different index values. In order to understand what is exactly that we are selecting, one easy way is to create a new material and under viewport display assign to it a distinct color. We can then add a set material node to the chain, select the newly created material and connect the result output of the equal node to the selection input of the set material node. In this way, we can again scroll through the different available selections, and if we type a value of 30, we can see that we are selecting exactly the top face of the drum. We can then remove both the material and the set material node and use our selection into the scale elements node. I will then drag an empty input into the scale value and then rename it to shaft tapering, and then assign to it a value of 0.8 as in our practical example. If you remember, in order for the tapering to work, we need to use an exponential function. Hence, I'm going to add a new math node and I'm going to set it to power. Then I'm going to use the tapering value as the base, and since the exponent needs to be incremental, we can simply use our index. In order to take into account both the tapering and the thickness, we just need to multiply the result of the power node by whatever value we are using for the thickness itself, and connect this to both the X and Y sockets of the combined XYZ node connected to the scale input of the instance on points node. In this way, we can use the two values independently and they will work just fine together. To finalize the node tree related to the shaft, I'm going to create yet another input parameter and connect it to the count factor of the mesh line nodes, and I rename it to number of drums. I'll then select all the relevant nodes and organize them into their own frame. We can now do a quick recap of what we have so far. So we can control the height of the shaft as well as the number of drums, we can define the thickness and the tapering, and we can define also the distance between each drum as well as their minimum and maximum sizes on the z-axis. Now the next step is to add a base and a capital to our column system, and for this purpose I'm going to import a few resources that I prepared in advance and I'll put them into my column collection. The important bit for all of these pieces is that they need to have the origin point right at the bottom and that they need to be standing exactly on the ground. I start by adding the base to the geonode system, so I'm going to enable my controller back, take the base and drag it into the node tree, and then I'll disable the column collection once again. I'll then add a join geometry node and I'm going to connect the base to the shaft. We do want our shaft to be sitting right on top of the base, which means that we will need to move the shaft by an amount which is equal to the size of the base on the z-axis. To do that, I'm going to add a transform geometry node and a combined XYZ node connected to its translation input socket. To get the real world scale of our base, we can use a bounding box node, which essentially represents a box wrapped around our mesh, where we can use the min and max output sockets to get the size of the mesh on whatever axis we may need. I'll add a separate XYZ node for both the min and the max, and in order to get the size of the mesh on the z-axis, we would just need to add a math node set on subtract and subtract the min z value from the max z value. We can now connect the output of the subtract node to the z socket of the combined XYZ node, and in this way the shaft will sit exactly on top of the base, whatever is the dimension of the model that we are using as the base itself. We then need to take into account that the thickness of the shaft needs to have an influence also on the scale of the base, and as such I'll add a transform geometry node once again and a combined XYZ node connected this time to the scale input socket. I'll then take my group input node and make a copy just to keep my tree a bit more organized, and I'll use the thickness value as the input for the X, Y, and Z sockets of the combined XYZ nodes. In this way, whatever is the value of the thickness that we are using, we can see that the base is rescaling accordingly. We can now proceed to add also a capital to the column system, and also in this case it is important that the mesh that we are using has the origin point right at the bottom and that it is standing exactly on the ground. So again, I'm going to enable back my controller. I'll then take the mesh which corresponds to my capital and I'll bring it into the geonode system. I'm going to connect this to the join geometry node and I'm going to disable the column collection in the outliner. To position the capital on top of the shaft, we will need to move it on the z-axis by an amount corresponding to the sum of the respective heights of both the shaft and the base. To do that, I'm going to add a math node set to add, and I'm going to feed into it both the shaft height input parameter and the result of the bounding box operation for the base, and I'll use this as the translation factor along the z-axis for the capital. Then, to account for the value that we are using as the gap between each drum, I also subtract from the addition that we just did the input value that we are using for the drum's gap. As we did for the base, we need to take into consideration also the value used for the thickness of the shaft into the scale of the capital. So once again, I'm going to feed the thickness input parameter into the X, Y, and Z sockets of the combined XYZ nodes connected to the scale input socket of the transform geometry node. Lastly, we need to adjust the scale of the capital by the tapering factor used for the shaft as well. And for that, I'll use a math node set to power, where the base will be the value used for the tapering, while the exponent, since the capital is sitting on top of the last drum, will correspond to the number of drums input parameter. We then need to multiply the result of this operation by the value coming from the thickness, and we should be good to go. We can now organize our nodes once again into a separate frame, and as a last step, I'm going to create an input parameter for all of the different models that we are using for either the shaft, the base, and the capital. Before moving on to the next step, let's do a quick check on all of the functionalities that we have implemented in our system to control whether they are working as intended. So again, we can control the height, thickness, and tapering of the column, as well as the number of drums, the gap between each drum, and the respective minimum and maximum sizes on the Z-axis. As a further check, I'm going to switch among the different models that I have prepared, in particular for the base and for the capital. If you, like me, have a desire for crafting unique tools, chances are at least one time you fancied about designing your own Blender add-on. Coding and programming languages in general, though, can be a scary learning experience, especially if you're a beginner, and that's where it becomes important when developing your skills that you rely on industry experts. In that sense, Skillshare, which is kindly sponsoring this video, is the largest online community designed by creatives for creatives. In its many classes, you will meet professionals that will share their tools and techniques, providing you with tons of resources and learning paths, like the one I found here for Python, that will bring you from novice to pro in no time. And what I found particularly interesting is that you can really learn at your own pace, since the platform is pretty well designed and it will let you save and resume your lessons with ease. Whatever is that you are into, whether it is illustration, graphic design, photography, music, or something else, on Skillshare you will find thousands of creative classes that will help you in becoming a master with a learn by doing approach. If you want to start investing in yourself today, check this link here and in the description. The first 500 people will get a 1-month free trial on Skillshare. We can now move on and talk about how to spawn different columns as to create like a sort of a columnade. And you may be tempted to think that once we have this system in place, it would be enough to add something like a mesh line node with an offset on either the X or Y axis and then use this node to generate some points upon which instance the result of our entire node tree. And while this is working, we can see that we have no randomness applied among our different columns. And that's because whatever is happening here, once it is passed on as an instance, it is simply going to be copied over and over. For this reason, I removed these nodes and we will take a look instead at the group ID function of the accumulate field node. What the group ID does is to split the instances, in our case the drums, into different stacks based on whatever logic is used as an input. To show how it works, I'll add an index node, and just remember that our index currently has 4 distinct values corresponding to the number of drums, since it is connected to the count factor of the meshline node. And when I use the index as the input for the group ID, what the accumulate field would do is to create 4 different stacks, one for each of our drums. At the moment, they are all overlapping at the center, so I'll add a math node set to multiply, and then multiply the value coming from the index by a factor, let's say of 2, and use this as the offset factor on either the X or Y axis. We can now clearly see the different stacks generated by the accumulate field node, where the number of stacks is currently tied to the number of drums. But this is not what we want, because we do not want to have one column for each drum, but instead we do want to have multiple drums for each of our shafts. And in order to do so, we need to change the logic applied to the group ID factor of the accumulate field node. For this purpose, I'll add a math node and I'll set it to truncated modulo. And what the modulo operator does is to take the value at the bottom and check how many times it fits the value at the top, yielding the remainder of the operation as the result. I'll use the index as the value at the top and preview the output of the modulo node, connecting as well the relevant piece of geometry to the viewer. What the modulo node is doing is checking how many times the value of 2 is fitting each of the values of the index, returning the remainder as the final output. So in this case, 2 fits 0 times into 0 with a remainder of 0, then it fits 1 again 0 times, but this time with a remainder of 1. Then it fits 2 exactly 1 time with a remainder of 0, then it fits 3 1 time with a remainder of 1, and so on. What we're doing here basically is creating a sort of a parallel index where the number of distinct values will correspond to whatever is used as an input in the bottom socket of the truncated modulo node. And once we pass the result of the truncated modulo into the group ID factor, what the accumulate fill node will do is to take all the instances with a corresponding value and group them together into a single stack. I'll now remove the viewer node, take the output of the modulo node and use it for the group ID of the accumulate fill node and for the offset as well. And we can now see that we have our two stacks corresponding to the value at the bottom of the truncated modulo node, and we can see that all of our drums are being distributed among the different stacks. The value at the bottom of the truncated modulo will then represent the number of columns, while the offset used in the multiply nodes will be the distance between each column. To define the number of drums for each shaft, I'm going to multiply the number of columns by a factor for which I reuse the number of drums input parameter and connect the result to the count factor of the meshline node. In this way, we can easily decide how many drums we want for each shaft. Moreover, whenever we spawn multiple columns, we can see that for each shaft we will have a random placement of the drums. To account for the number of columns, also with regards to the base and to the capital, it will be enough to add a meshline node where the count will be equal to the number of columns and where we can use the distance between each column as the offsetting factor on the y-axis. We will then need to add an instance on points node to generate the points upon which we will instance the original geometry. And finally, we just need to replace the original connection with the output of the instance on points node. I'll do the same also for the capital, and finally we will need to adjust the tapering since by using the group ID function of the accumulate fill node, the original methodology is not going to work anymore. And the reason why is pretty simple in that we are currently using the index as the exponent, and while the index is a sequential series of numbers, we can see that the grouping performed by the accumulate fill node is non-sequential. And in particular, we want to have an exponent of 0 for the first instance in the first group, then an exponent of 1 for the second instance in the first group, and so on, and the same should apply also for the second group and for all of the other groups that we may have. And in order to go from the current exponent to the desired exponent, we need to try and look for a pattern. And in this case, we simply need to subtract from the index the output of the truncated modulo and divide the result by the number of groups or stacks that we have. To replicate this into the node tree, I'll take the index, then I'll add a math node and I'll set it to subtract, and I'll subtract from the index the output of the truncated modulo. Then I'll add another math node and I'll set it to divide, and I'll divide its result by the number of groups, which correspond to the number of columns. Finally, I will simply need to take the output of the divide node and use it as the exponent. Now that the column system is in place, we can reuse some of its concepts, especially those linked to the accumulate fill node, to be the sort of a template. We can then use that to generate either horizontal or vertical stacks starting from a defined mesh and with the same random capacity in relation to each instance size, similarly to what we did for the columns shaft. I leverage on these templates for the next part, which is about building a procedural vault. Let's see how to approach that. I've created a new collection placed within the main one, which is the one holding all the items that I'm using in my GeoNode systems. Within the new collection, I have placed a couple of meshes that are used in order to create the coffer structure of the vault. In both cases, the dimensions for both the Y and Z axis are set equal to 1 meter, the origin point is right at the bottom left corner, and the mesh is placed exactly on the ground. Additionally, if we tap into Edit mode, we can see that I added a few extra edge loops in order to help with the bending process that we will have to perform in a minute. With this in place, I created as well the controller that will hold the system, and with this selected, I'm going to click on New and I remove the existing connection. I'll then take one of the two meshes, bring it into the GeoNode system and disable its collection in the outliner. As a first step, I'm going to stack my mesh uniformly on the Z-axis, and for that, a simple meshline node will do. I'll use the meshline node to generate some points, then I'll take my mesh and I'll connect it to the instance socket, and I'll then connect the result of the instance on points node to the output of the GeoNode system. To generate the iterations also on the y-axis, I'm going to duplicate the instance on points node and then rewire the output of the first node into the instance socket of the second node. To generate the new points, I'll then duplicate the mesh line node with the offset this time on the y-axis, and to give our object the usual shape of the vault, we will need to bend it on the y-axis as a whole. To do that, we will need to convert all of the different instances into a unique mesh, which we can do by adding a realize instances node. I will add as well a merge by distance node, which will connect all the different pieces together, and at this point, from the modifier stack, we can add a simple deform modifier set on bend on the y-axis with an angle of 180 degrees. Back into our GeoNode system, it is now clear that the count of the first meshline node will represent the width of the vault, while the count of the second meshline node will represent its length. Hence, I'm going to create two new group input parameters and I rename them accordingly. I'll now add the arch profile to both the front and back of our vault, and for that, within the vault collection, I already have a mesh in place, also in this case with a size of 1 meter on the z-axis and with the origin point right at the bottom. Moreover, I already placed it into position with respect to the mesh used to create the vault, and also in this case, I'm going to tab into edit mode and add a few edge loops to help with the bending. I'll then go back to the geometry node system and I'll disable the simple deform modifier for now. To add the arch profile to the vault, I'm going to leverage on one of the utilities that I have created, and in particular I'm going to add a vertical stack where I'll select the arch profile as the model that I'm using. I'll then add a join geometry node right before the realize instances node, and I'll connect my arch profile to the rest of the geometry. I'll then set the length of the stack equal to the width of the vault. I'll bring the gap up to something like 0.02, the number of pieces down to something like 6, and I'll also increase the max piece size to something like 2. If we now enable the simple deform back, we can see that everything is right where it is supposed to be. Now, in order to create the other side of the arch profile, I'll go back into the vault collection, select the profile mesh, and I'll add a mirror modifier on the y-axis and I'll disable the merge option. I will then apply the modifier, tab into edit mode and deselect everything, and then move my mouse over the new object and press L and P to create a new mesh. In the geometry node system, I'll duplicate the original vertical stack with Ctrl Shift and D in order to keep the existing connection in place. I'll then select the new mesh and connect this as well to the rest of the geometry. Finally, we will need to move this new profile to the other end, and to do that, I'm going to add a transform geometry node with a combined XYZ node, and the offset factor on the y-axis will be equal to the length of the vault. We can now do a quick test of what we have and add a few input parameters to the system as well. With our system ready, I want to show you a way in which we can make different geometry node systems communicate with each other. As a test case, I want to build the wall surrounding the vault, and I want to do that procedurally by rescaling a cube to the desired size and then using the Boolean operator to restore the inner part of the vault. To do so, I created a cube with a dimension of 1 meter on all of the three axes, with the origin point right at the bottom and located at the same spot at which we originated the vault. We now need to get access to both the width and length input parameters used for the vault itself. And to do that, we can go into the original geometry node system, take the group input node, make a copy, and then we can simply create group output parameters for both the width and the length. And then under output attributes, I'll simply rename them accordingly. Now, to manipulate the cube, I don't want to use the original geometry node system because I don't want any of the deformation applied to the vault to be applied to the cube as well. For this reason, I'm going to create a new geometry node system right after the simple deform. I'll then click on New, and I'm going to bring my cube into the new system and I'll disable its collection from the outliner. To connect the cube to the rest of the vault, I'll use a join geometry node, and now the idea is that I want to move the cube to the center of the vault, whatever the size of the vault itself is. To do that, I'll use a transform geometry node and a combine XYZ node connected to the translation input socket. To get the right amount for this translation, we need to retrieve both the length and width of the vault, and we can do that with a named attribute node, through which we can look for the desired attributes. Now, the output of this node does not represent a single value, but it is more like an array of values where the length in this case is repeated identically for all of the iterations of the index. To turn this into a single value, we need to use a sample index node, and whatever value for the index will be fine. Then I'll connect the attribute to the value and the geometry to the geometry socket. I'll then repeat the same operation to get also the width of the vault, and now if we look at our original problem, what we have is a semi-circumference represented by our vault, and then we have a cube which is lying at some point along the circumference which we want to move right at the center, where this distance is going to be the radius of the entire circumference implied in our vault. Since the value of the radius is the circumference divided by 2 times pi, I'm going to add a math node set to multiply, and I'm going to multiply the width value, which is half the circle, by 2. Then I'll add another node, this time set to divide, and I'll divide the output coming from the multiply node by 2 times pi. I'm then going to frame this couple of nodes and rename them to radius, and I'll use the output of this combination for the translation factor of the cube on the x-axis, while for the translation along the y-axis we simply need to get the length of the vault and divide it by 2. Hence, I'm going to add another math node, set it to divide, then take the length attribute, divide it by 2, and then I'll use this as the input for the y socket of the combined xyz nodes. In this way, whatever values we are using for the width and the length of our vault, you can see that the cube is going to stay right at the center of the vault itself. To manipulate the scale of the cube, I'm going to add yet another combined XYZ node, this time connected to the scale input socket of the transform geometry node, and then I'll add 3 math nodes set to multiply, one for each of the 3 axes, which I'll use to multiply whatever attribute we want to use for the scaling of the cube on that specific axis by a multiplicative factor to be used as an input parameter. For the y-axis, I'll use the length of the vault with a multiplicative factor of 1, while for the x-axis, I'll take this time the width, again with a multiplicative factor of 1. Finally, for the z-axis, I'll take the size of the radius with a multiplicative factor, this time of 1.5. For the next step, we need to make sure to remove the portion of the cube standing within the inner part of the vault. For that, I'm going to enable back my vault collection and I'll then add a cylinder. I rescale it in order for it to be 1 by 1 by 1 meter, and I rotate it on the x-axis by 90 degrees, and then I right-click and shade smooth by angle. We need then to apply all the transformations, bring the cylinder within the geonode system, connect it to the join geometry node, and disable again its collection from the outliner. For the translation of the cylinder, I'm going to reuse what we did for the cube. Hence, I'm going to add a transform geometry node and reuse the output of the combined XYZ node into the translation socket. For the scale, I'm going instead to create a new combined XYZ node with the 3 elements set to 1, and I'll connect it to the scale input socket. I'll then add a couple of math nodes and I'll set them both to multiply. Now, for the dimension of the cylinder on the y-axis, I'm going to use the length of the vault, and since I want it to be sticking out of the mesh a bit, I'm going to multiply this by a value greater than 1, let's say 1.3, and connect the result to the y-socket of the combined node. While for the dimensions on both the x and z axis, I'm going to use the radius multiplied by a factor of 2. I'll then remove the connections of both the cylinder and the cube to the join geometry node, and I'll add a mesh boolean node set to difference where I'll connect the cube to the top and the cylinder to the bottom and connect this to the rest of the geometry. Since the original vault is still not visible, it means that we need to increase the size of the cylinder on both the x and z axis. To do that, I'm going to add another math node set to add, and I'm going to add a factor of 0.5. Let's speak for a moment about walls. Using textures, of course, is usually the most efficient way to handle them. But still, now that we explored how to randomly build different stacks, I want to show you how to apply this as to create a procedural wall system. So again, I got my building block, which is a simple cube with a dimension of 1 meter on all of the 3 axes, standing on the ground and with the origin point right at one of the extremities. I got my controller as well, and with this selected, I'm going to create a new geometry node system. I'll then remove the existing connection, and for this I'll leverage on my horizontal stack group, and as such with Shift A I'll add one horizontal stack and then connect this to the output. I'll then select my wallstone model as the base piece, I'll give it a length of 8 meters for now, and I'm then going to create a unique copy of this group by clicking this icon here and renaming it to wall generator. The first step is to create the vertical iterations for our wall, and we know from the column part that for this we will need to use a truncated modulo node. Hence, I'm going to add an index node and a math node set to truncated modulo, and I'm going to connect the index at the top, while for the value at the bottom, I'll create a new group input parameter renamed to wall height. I'll then connect the output of the truncated modulo to the group ID of the accumulate fill node. Now we need to offset the newly generated stacks on the z-axis by an amount equal to the height of the wallstone piece, which is currently 1 meter. So I'm going to add another math node set to multiply, and again I'll multiply the output of the truncated modulo by 1 and connect this to the z socket of the combined xyz node that we are using to translate the points generated by the meshline node. For the moment, I'm going to set the height to 4 meters, and you can see that we have all of the 4 groups stacked on top of each other. Suppose now that we want to control the height of the wallstone piece, what we could do is to create another group input parameter and connect it to the z socket of the combined node used to define the scale of each instance. I'm going to rename this to stone height, and I'll give it a value of 0.6. We need to account for the height of the wall stone piece also when defining the offset on the z-axis of all of the different stacks. To do that, I'll use the stone height input parameter at the bottom of the multiply node that we just used to translate the points generated by the meshline node. Moreover, we may want to adjust the offset on the z-axis also by whatever value we are using for the gap between each piece. So suppose I want to use a gap of 0.05, you can see that currently it is applied only horizontally. To amend that, I'll add a math node right before the multiply node, set to add, and I'm going to add to the height used for the stone the input parameter used for the pieces gap. At this point, I want to redefine the number of pieces that we are using for our wall as a function of the area of the wall itself. Hence, I'll disconnect the number of pieces input parameter from the count factor of the meshline node, and I'm going instead to add a multiply node where I'm going to multiply the length and the height to get the area of the wall. I'll then connect this to the count factor of the meshline node, add another multiply node, and reconnect my input parameter, rename to number of pieces multiplier, and I'll set this to float with a default value of 1. In this way, apart from having control over the number of pieces, we can also have the number of pieces adapting dynamically to whatever is the length or height of our wall. I now want to apply a bit of a random rotation for each of the instances which are composing our wall. To do that, I'll add yet another combined XYZ node and then connect it to the rotation input socket of the instance on points node. We can use this to rotate our instances on whatever axis we want, and since I want to do that randomly on the z-axis, I'm going to add a random value node connected to the z-socket of the combined XYZ nodes. The result is overly exaggerated, so to tone it down a bit, I'll define a starting value, which in my case will be 0.01, and I'm going to connect this to the max input socket. Then I want the rotation to be applied also on the other direction, so I'll take the same value and pass it through a math node set to multiply with a value of -1, and I'll connect this to the mean input socket. To control the strength of the random rotation, I replace this value node with a group input parameter renamed to random rotation strength, and through this value we can effectively control the amount of the random rotation which is applied. One problem that we have is that when we increase the rotation strength, you can see that we are creating some gaps between the various instances, and that's because each instance is rotating around its origin point, which is currently set here at the bottom. I'll then go back to my wallstone piece and I'll move the origin point at this vertex here at the front. For that, I'll tab into edit mode, select the vertex, move the cursor to the vertex, then right click and set origin to the 3D cursor. I'll then move the cursor back to the center of the 3D world and I'll move my mesh as well back to where the cursor is. If we now go back to our system, we can see that this will allow us to have a much more organic random rotation for all of our pieces. What we have so far is fine if we need a simple wall facing only one direction. But what if we want to create a sort of a cornered wall? In that case, we would need to create some gaps to represent the intersections to be used by the different pieces of the wall structure in order for them to blend correctly. To do this, we need to offset the different stacks on the y-axis following a particular kind of logic. And what I mean is that, for instance, I want the first stack to be offset by 1, the second stack to be offset by 0, the third stack to be offset by 1 again, and so on. We can then use again a truncated modulo node, so I'll make a copy, use the index at the top, while for the bottom socket I'll type a value of 2, which means that it will only return zeros and ones. To make use of its output, I'll add another math node in between the multiply node and the combined XYZ node used to move around the points generated by the meshline node. I'll set this new math node to add, and I will take the output of the truncated modulo node and place it in the bottom socket. The idea here is to simply create the other section of the wall by duplicating the node that we already have, then join it back with the rest of the scene with a join geometry node. We then need to translate it on the y-axis, hence I'll use a transform geometry node and a combine XYZ node connected to the translation input socket. The value that we will need to use as an input for the translation is simply the wall length plus 1. For that, I'll create a new group input parameter, drag and add a math node set to add with a value of 1, and then connect this to the Y socket of the combined XYZ node. We will then need to subtract whatever value we are using for the gap between each piece. So again, I'm going to add another math node, this time set to subtract, and then I'll subtract the piece's gap value. Finally, we will need to rotate the second section of the wall by 90 degrees on the z-axis. To have more control also over the width of the wall, what we can do is to create another group input parameter to be connected to the wall length of the second section and rename this to wall width. In this way, we can control the length and width of the wall independently. We now have a few systems ready to create columns, vaults, and walls. Everything is looking fine, but there is one big element which is still missing. In fact, there is no classical ruin scene without ruins, of course, and as such, let me show you a method to create procedural damage on your assets without using any external add-on. The idea here is pretty simple. We are going to take a mesh, make a higher poly version of it, then move its vertices randomly but in an organic way, and get as the final output the intersection between the new mesh and the original one. So, to create the higher poly version, there are a couple of ways. The first one is to use a subdivision modifier. The point of the subdivision modifier, though, is that when we do not have uniform topology, the result of the subdivision is going to be non-uniform as well. The other way to create the high poly version is to remesh our object, and we can do that either using the remesh modifier in the modifier stack, or, and this is the way I prefer to do it, we can do that directly within the geometry node system. For that, we will need to convert our mesh into a volume and then convert the volume back into a mesh. In this way, you can see that we have uniform topology despite the shape of the object, and we also have access to this voxel amount number, which will represent the resolution of the high poly mesh. To move the vertices of the high poly mesh, I'm going to add a set position node right after the volume to mesh node. Our aim here is to move the vertices randomly but in an organic way, hence I'm going to leverage on the normal information for each of the vertices, and then I'll add a random element which could be represented by a noise texture node. To put the two elements together, we can use a vector math node set to multiply, and we can feed the output of this vector multiply node into the offset socket of the set position node. I'll then add a math node right after the noise texture node set to multiply, and this will allow us to control how far the vertices are traveling along their normals. The final result of the node tree needs to be the intersection between the displaced mesh and the original mesh, and for that I'm going to use a mesh boolean node set to intersect, where I'll connect the two pieces of geometry and then connect the output of the mesh boolean node to the output of the node tree. A decisive role here is going to be played by the multiply factor. In fact, if the displaced mesh is too big, only the original mesh is going to be visible, since it will be entirely comprised within the first one. And the same, of course, is also true the other way around. Once we have identified the desired offset for the noise, another useful thing is to add a map range node in between the noise texture and the multiply node. And in this way, we can control the amount of the damage by darkening the shadows, as well as the sharpness by brightening the highlights. As a last step, I'm going to change the noise texture from 3D to 4D so that we can directly control the pattern of the damage, and I'm going to tie the pattern itself to the position of the object multiplied by an input factor. We can then group all the nodes together, creating as well some input parameters. In particular, I want to have an input parameter to drive the resolution of the damage, then I want one input parameter to control the offset and another couple of parameters to control both the amount and the sharpness. Then I want to be able to control the scale of the damage, which I can do by using the scale input value of the noise texture node. Finally, I'll create another input parameter to control the factor used in defining the pattern. Now, the best way to use our procedural damage would be to apply it to the final scale of the object in order to avoid any potential stretching, especially when we are pushing the size of each individual piece very far from its original dimension. So to do that, it means that we would need to apply the geometry node system that we use to build the object itself, and in this case I would need to add a realize instances node and then Ctrl A to apply the system. Additionally, we cannot apply the damage on the object as a whole, since the remesh operator would result in a blobby mess. So to make each piece a separate object, I would tab into edit mode, select everything, and then under mesh, separate by loose parts. Then again, with everything selected, I would place the respective origin points at the center of each individual geometry by right-clicking and set origin to geometry. We can now select one of the pieces, create a new geometry node system, and add the damage generator node. We can then as well change a few parameters, like decreasing the resolution and increasing the amount of the damage, and then, to apply the modifier to all of the other pieces, we can shift select all the pieces which do not have the modifier applied, Ctrl left click the piece with the modifier applied, and then Ctrl L and copy modifiers. This method allows for the highest degree of freedom and customization when it comes to damage, but it is destructive in the sense that we lost access to the original geometry node system that we used to build the object itself. A non-destructive method to apply the damage would be to go into the original geometry node system, then take the mesh which is represented by this object info node and apply here the damage generator node. The only problem that we have with this approach is that the pattern is repeated identically for all of the instances. So to create a few variations, we could create some duplicates of the damage generator node, changing a few parameters here and there, and then we could connect everything into a geometry to instance node and then connect this to the instance socket of the instance on points node, activating also the pick instance option. In this way, we can keep our original geometry node system intact and we can still have a few variations in our damage pattern. Suppose that we now want to change some of the parameters of the original geometry node system, like perhaps the length of the stack or the number of pieces. The process can become quite slow depending on the number of instances, so in order to solve that, what we could do is to add a switch node and connect a new group input parameter to the switch socket. We could call this useDamage, where if it is true, we are going to connect the output of the geometry to instance node, while in case it is false, we are going to connect the original piece of geometry. And then we can connect the output of the switch node to the instance socket of the instance on points node. You can see that in this case everything is disappearing, and that's because the pick instance option needs to be enabled only in case we are using the output of the geometry to instance node. So again, we can create another switch node, this time set to boolean, and we can connect again the input parameter that we used for the first switch node into its switch socket. Then we can create a couple of value nodes, one set to 0 in case it is false and one set to 1 in case it is true, and then connect the output of the second switch node to the pick instance socket. In this way, we can manipulate the parameters of the original geometry node system in the way we want, and once we are happy with the result, we can simply click the Use Damage checkbox. I applied the same approach to all of the other elements as well and built a couple more pieces with the same techniques used also for the other assets, like these profiles and the procedural staircase, where the length and width would be in this case driven by the measures of the controller itself to ease both its sizing and placement. It is now time to test all of this into a real scene. I used as an inspiration a painting by Hubert Robert, which is not the most complex but still allows for the testing of a few different workflows. One possibility is to integrate different geonode systems into one another, as I did for instance to replace the cube used to mimic the walls of the vault with a much proper wall system. The other option is to simply combine the different systems as you would with simple standard meshes. To create gaps into the structures, one trick is to use a delete geometry node set to instance and a random boolean node to drive the probability of the pieces going missing. For the entrance part, I simply manually scattered a few stones and columns drums here and there and then applied a bit of a displacement to the ground floor. Then I used the Geoscatter add-on to add even more rocks and grass, using vertex groups to create a sort of a path leading to the main entrance. It was then time to start adding damage to the meshes. Also in this case I followed a couple of approaches. I would either apply the damage system to each piece separately, as in the case of the profiles or of the staircase, where I wanted to avoid the overstretching effect of the noise texture driving the damage, or instead leverage on the Use Damage checkbox for those meshes where it was safe to use it. For the texturing part, I repurposed my own procedural marble material, thus avoiding the need for any UV unwrapping. I simply tweaked some of the parameters and employed the random per island output of the geometry node to create a sort of a mesh-by-mesh color variation. Along with that, I also imported a few grunge maps for both the albedo and normal maps, and to have a more distinct separation between the foreground and the background, I used a simple plane and played around with the alpha value of its material. Finally, it was time to test different HDRIs to reach the desired look and feel. I hope this video brought something new to your plate that you can reuse in your future projects. For now, thank you for watching and see you next time.